If we assume, starting here, that W sub x is actually greater than Fs max, then there is not enough static friction to keep the object stationary. It's going to slide. What kind of friction do we have? We have kinetic friction. So, what is the net force in the x direction? The net force in the x direction will be W sub x minus Fk, but what is the kinetic frictional force? It is mu k times the normal force, which is mu k mg cos theta, which leaves us with the force in the x direction is the W sub x, the component of the weight in the x direction, mg sine theta, minus kinetic frictional force, which is mu k mg cos theta. We can factor out an mg here and write this as mg times sine theta minus mu k cos theta. And we know this must equal, if this is f sub x, this must be the net force in the x direction. This must be the mass times the acceleration in the x direction. Dividing off the m, and we have, finally, a sub x equals g sine theta minus mu k cos theta. Very good. Now, one thing let me point out here. If you put in some value here for theta and mu k, and you get some positive value, there's your acceleration. If you were to put in numbers here, and actually because of this difference here, you were to get a negative acceleration, what is that telling you? A negative acceleration means an acceleration in the negative direction, up the incline. Does that make sense? It does not make sense. So, if you put in numbers and get a negative value here, you know something is going wrong. Well, what does that mean? When would this give you a negative value if this were bigger than that? In other words, dividing by cos theta when mu k is bigger than tan theta. Well, we know mu k can't be bigger than tan theta because mu s is not bigger than tan theta, and mu k is less than mu s. So, what that is telling us is that there is not enough friction to keep it in place, so this quantity has to be a positive number. A very, very interesting result that we can get without even putting any numbers in and just using variables for the very end. Okay, very, very good. Let's try one more problem. And again, we're just going to use variables. We're not going to put any numbers in it. Let's imagine that we've got a mass sitting on a horizontal surface, and someone comes along and starts pushing on it, but now they're not pushing on it horizontally. Let's imagine they're pushing down to try and get it to slide. Not a very smart thing to do. You really should push horizontally to get as much of your push in the horizontal direction as possible, but let's imagine this person is pushing with a pushing force that is at an angle of theta below the horizon. And again, we'll assume that there is friction, mu k and mu s coefficients. Let's look at this very generally and see if we can figure out what could or what might happen in this case. What forces do we have now in our free body diagram? Well, we've got our pushing force down at some angle theta. We've got the weight. We've got the normal force. And we're going to have some frictional force. And because the motion would be this way if there were any motion, the frictional force is going to oppose that and is going to be back in this direction. So again, let's break this down into x and y, horizontal and vertical. Again, horizontal and vertical because if there's any motion at all, it's going to be along the incline, horizontal, so we'll define one axis in the direction of possible motion and then the other axis perpendicular to that. So what forces do we have in the y direction? Well, in the y direction we have the normal force in the positive y direction. We have the weight in the negative y direction. But then we also have a component of the pushing force. The y component of the pushing force will be, let's do this a little bit shorter, say F sub p rather than F push. Fp sine theta. So we have an Fp in the negative y direction. So we have a minus Fp sine theta. We know there's going to be no motion in the y direction, so this must all equal may, and ay is 0, so we know this whole thing must be 0. Which means the normal force is mg plus, bringing these to the other side, Fp sine theta. Now this makes sense. The normal force has to balance the weight for one thing, but then it's going to balance part of the component, it's going to balance a component of the pushing force. Whatever is pushing down, that's going to increase the normal force. And how much is pushing down? Well, that's the Fp sine theta. So the normal force is increased by an amount Fp sine theta. What are the forces in the x direction? Well, we've got the pushing force, Fp cos theta, but then we're going to have the frictional force in the negative x direction. So we're going to have a minus F. So what's going to happen? Are we going to have an acceleration or not? Well, what we have to do is compare this Fp and F, the frictional force. But what's the frictional force? What can it be? Well, what's the maximum value the frictional force could be? It could be Fs max. What is Fs max? It's mu s times the normal force, or mu s, but now the normal force is mg plus Fp sine theta. So let's compare this force with the Fp cos theta, this part. We're going to compare the maximum value that can be and this part, Fp cos theta. Now notice, when theta is small, when theta is, let's say, 0, sine of theta is 0, and we have mu s mg, and cosine of theta is F push. And we're just comparing the pushing force with mu s mg. That's what we had when we were looking at just a horizontal case. As theta increases, sine of theta increases, but cosine of theta decreases. So what happens? The maximum static frictional force increases, while the component of the force actually pushing it along in the horizontal direction decreases. Eventually, perhaps, if the pushing force is large enough, and we're assuming it's going to be large enough to overcome the static friction, usually, if you're actually trying to push something, it's not going to be a small force. But if the pushing force is large enough to overcome the static friction, if theta is large enough, this term will actually be larger than this term. And even if it doesn't matter how hard you push, this could still be larger than this. If Fp sine theta is larger than Fp cos theta, it doesn't matter how much friction you have. Well, no, I take that back. It does depend on how much friction you have. But if Fp is large enough and theta is large enough, this term with the mu s could be larger than this term. And what's going to happen? Well, then you will not overcome static friction. So let's take a look just at a little example of that. Let me take a little drink. Here I have a board on a horizontal surface, and if I push horizontally on it, I can make the board slide fairly easily. But imagine I'm pushing down at an angle. If the angle is small, I can still move it. But if I increase the angle too much, it doesn't matter how hard I push, and I'm pushing much harder than before, I still cannot move it. But if I decrease the angle, then excuse me, the block starts to slide. So what we see here then is a much more complicated relationship between excuse me, the direction of push and how much friction we end up with. All right, very, very good. Well, let's assume that our pushing force in the direction of motion is larger than our maximum static frictional force. So what happens in that case? Our friction is kinetic. In Fx, this will be kinetic friction. The value of our frictional force, and I can just change this right here, will be F sub k, will be mu sub k Fn, which is mu sub k mg Fp sine theta, which leaves us with our net force in the x direction is Fp cos theta minus Fk, so minus mu k times mg plus Fp sine theta. That is our net force in the x direction, and what must this equal? This must equal ma(x). So we can then find what our acceleration in the x direction is by dividing by m, and we find ax equals Fp cos theta minus mu k mg plus Fp sine theta, all divided by m. Very, very good. Let's look at this in some extreme situations. What do we have when theta is equal to 0? When theta equals 0, we have basically the pushing force is horizontal. It's going to be perfectly horizontal. What do we have? We have theta, sine of 0 is 0. Cosine of theta is 1. And we'll end up with Fp minus mu k mg all divided by m. But that's exactly what we got when we were looking at just a horizontal pushing force acting on an object with friction. It's the pushing force minus the kinetic frictional force, and then the whole thing divided by m. Well, that makes complete sense. What about if theta gets large? Or what if theta gets much, much larger? Well, what happens? Well, cosine of this is going to get smaller. This will get small. Fp sine theta, this will get large. Eventually, this term is going to be larger than this one, and we're going to get a negative result. Well, what does that mean? Like we saw before, a negative acceleration means the object is going to accelerate this way. No, that doesn't make sense. So, theta cannot get so large that the mass is not going to accelerate in the negative direction, so there is a maximum value for theta, and that will be when these two terms are equal to each other. Well, that makes sense. Very, very good. Okay, that's enough for today, I think. Next time, we'll start looking at some more examples of forces and applying them to situations with Newton's laws and figure out what kind of motions will we get in that case. Okay, see you next time.